post this afterwards. So recording started. And okay. Can anyone else hear me by any chance? Okay, cool. Cool. Alrighty. Well, then I'll go ahead and okay. Can you see the PowerPoint okay online? Maybe. Yes. Okay. Okay. Well, if for some reason you can't see the PowerPoint or anything, just feel free to just unmute and speak up. So, because I won't be able to see the chat while I'm writing. So, all right. Okay. So I'll go get started. So Dr. Vassal asked me to work through the practice exam. So there's 5 problems. The 5th one is extra involved. So I'll probably kind of like go a little bit quicker the first 4, and they're a little bit shorter, less involved, and I'll spend more time on the 5th one. So if you have questions, just speak up, let me know. And if I'm going too fast, let me know too. But that's the reason why I'm going to go faster in the beginning. The problems? I think he did, but I have them on here too. The prompts. So if you don't find it, just let me know, and I'll tell him to upload it, or I can send you the PDF too. So, alrighty. So, make sure I can write okay on here. Yeah, sweet. Okay, so problem 1 is an airplane is flying at 270 meters per second. At what altitude in the standard atmosphere will the airplane's Mach number be? Actually, this is a typo. It should be 0.8 is the Mach number. So that is a correction there. So Mach number is 0.8, and we're going to use the tables that are provided on Canvas to solve this. And just so you know, Dr. Vassal said that there will be a formula sheet and tables provided during the exam. So you'll have those whenever the exam is. Okay, so let me okay. So I'm going to write my givens real quick. So given, we don't have a lot of givens here, but we know that the velocity of this plane is 270 meters per second. And we know that we have tables available to us. Okay, so tables on Canvas, and we are looking to find the altitude. I'm going to call the altitude h, just to give it a variable. So the altitude h that is in a standard atmosphere. So maybe that's good to note that this is a standard atmosphere. So we'll just write that down. And we want to know the altitude h where the Mach number is going to be 0.8. Okay. So for the solution, I'll write over here on the right-hand side. Okay, so for the solution, I'm going to grab my notes as well to make sure that I'm going to write down every step that I did when I was working these. Okay, so for the solution, we know that the Mach number is equal to the velocity of the plane divided by the speed of sound. And so the approach to this problem is if we can find out what the speed of sound is at whatever this altitude is going to be, then we can use the speed of sound to, hey, welcome. We can use the speed of sound to reference to our table that's provided on Canvas, and the speed of sound will correlate to an altitude of flight. So if we use this equation, we can rearrange and say that speed of sound is equal to Mach number multiplied by velocity of the plane. And so then we know that the speed of sound is going to be oh wait, no, I just did the algebra completely wrong. So this would be velocity divided by the Mach number. I just rearranged that incorrectly. So then we know the speed of sound will be 270 meters per second divided by a Mach number of 0.8. Okay, and then that is going to equal to a speed of sound of 337.5 meters per second. Okay, so then if we reference to table A4, which is right here, this is what will be provided to you, and this is on Canvas as well. Then if we know we have this 337.5 meters per second, we can look at this table at, I'll circle it. It's this section right here. Oh no, this section right here. Okay. And so we see that we have a 338.4 and 336.5 meters per second. So this value is falling in between there. So what we need to do here is we need to do a linear interpolation for this. So we can, the way that I do it is I start by denoting what our 3 points are that we're going to use. So we have 500 meters of altitude, and that corresponds to 338.4. And then we have 1,000 meters of altitude, and that corresponds to 336.5. And then we have some unknown altitude. I'll call it H, because that's what I said it was earlier. And that corresponds to this 337.5. Okay, so then what we're doing is we're ratioing the slopes, right, of these points. So I'm going to say that on the left-hand side ratio, we will have H minus 500 divided by 337.5 minus 338.4. And on the right-hand side, we will have 1,000 minus 500 divided by 336.5 minus 3, well, if you'll let me write, 338.4. Okay. So if we calculate that real quick, then on the right-hand side, that ratio is going to be this. to 63.158. That will be multiplied by this. And then add 500. And we get the altitude is 736.842 meters. All right. So are there any questions on that one at all? Anything I could explain better, maybe? Or no? Okay. Well, if there are, just interrupt me and I'll go back. Okay. So for problem 2, I'm going to skip problem 2 and come back to it. I got distracted on the way here, and there's something that I need to look into with problem 2, so I'll come back to it. Oh yeah, sure. Yeah, this part. Sure. Yeah, no problem. Okay, so I'm going to wrap back around to problem 2 and go ahead and go into problem 3. Okay, so for problem 3, the velocity profile here is given to us. So we have this velocity profile, and we have a variable b that we want to know what the units are. There was one like this in the past on the homework. And so we want to know the units of b, and then we also want to find an equation that defines the shear stress in the flow. Okay, so our givens, we know our velocity profile, and that's u up that way. And then that's our only given. So then our finds, I'm going to do part A and part B here. Part A is the units of B, and part B is an equation for the shear stress. Okay. Alrighty. So for the solution, okay, so for part A, what I'm going to start by doing is just to list the units of each one of those quantities, and then we'll start, manipulating that and moving stuff around. So for this part, what I'm going to do is say u is a velocity, so that'll be meters per second, and that's equal to b times delta P is going to be a difference in pressure. So that'll be pascals or newtons per meter squared. You said it's a pascal. And then that's divided by viscosity, which is kilogram per meter second. Kilogram per meter second. And then we know that we have this difference of y values, and y is a distance measurement. So then y squared is going to be meters squared, since y is in meters. So this is a meters squared here. Okay, so then if we start canceling units, combining things, then we will see that this meters squared and that cancel. And so then let's rewrite this. So then we can say that meters per second equals B times a Newton is a kilogram meter per second squared. So I was going to write that. That's multiplied by meters seconds, moving up the denominator of the denominator, and then divide that by, by kilograms. This pen is giving me a hard time. Half the stuff I write doesn't even show up. So, all right. Okay, so then we start canceling stuff, and kilograms cancel, and we see that we have one of these seconds will cancel, and then we can cancel the other second with the second on the other side, and then one of these meters will also cancel. So we see that we have 1 meter left, and so this is looking like this. 1 is equal to B times meters, which is going to give a final answer of B is 1 over meters. Okay. So that is the answer to part A. And so I'll switch pages. We'll do part B. So for this part, we know that we want an equation for shear. We know that shear is viscosity times the velocity profile, du dy. So we have our, we know that our velocity profile is this B delta P over mu times y naught squared minus y squared. So I'll write that here. Delta P over mu y naught squared minus y squared. Okay. Yeah, I got that right. Okay. So then what we want to do is we want to figure out what is du dy, right? So then du dy is just the derivative of u with respect to y. So b delta p over mu is a constant term. So we'll just treat that as like on the outside of this integral, or this derivative, I mean. So we might say, okay, we might write it like this: b delta p over mu d over dy of y naught squared minus y squared. Okay. Now y naught squared is also a constant, so the derivative of that is just 0. So then this is going to be equal to b delta p over mu times 0 minus 2y. And now we just distribute our constant term, and this will be b delta p 2y negative divided by mu. So now, knowing that, we can say that our shear equation is equal to mu times what we just found there, negative b delta p 2y over mu. Cancel the mu's, and we get our shear equation is negative 2b delta p y. And that's that. Are there any questions on that one?
Yeah, can you show the part A, please?
Yeah, sure. Is there anything I can explain better there for you?
For the exam, would he offer a question similar to this, or is it just going to be a range of questions from all the things we've been learning in class?
I'm not sure. He didn't tell me what will be on the exam. He just said that this is the practice exam. So I would imagine that this is fair game for the exam. But
Okay. Okay.
yeah, I'm not sure if he'd tell me, what he's going to put on there. But seeing as this is the practice exam, I would say this is fair game.
Thanks.
Yeah, no problem.
I have another question.
Okay.
So,
Yeah, go ahead.
when it comes to the answer, also m to the -1 or inverse meters to -1 or inverse of meters would count as well
Yes.
in this case.
Yes. So you could say B equals meters -1. Also, that's valid.
And from what I've heard, he said, look at this, the homework questions, the recitations, and what he has in the PowerPoint. Like he
I say
said
that again.
regarding with the exam, like he said, he was suggesting look at the practice exam, the homework questions, and what's on the PowerPoint plus the recitation session.
Yeah, I would say whatever he's given you, homework, class stuff,
Because anything is possible.
Yeah, I'd say that's a good strategy. Go ahead and look at just everything he's given you. If he said that in class, yeah, that makes sense to me. Yeah. Do you have any other questions related to that? Okay. And then what was your question?
Oh, I think I figured it out. I was wondering where you got the second squared when you went down, but you switched the newtons to kilograms.
Mhm.
Okay.
Yes. Yeah. So this guy. Oh my. Okay. So this guy right here. That is just your Newton. Yeah. Okay. Well, if there's anything else with that, let me know. But yeah. Yeah, the second part.
So you weren't using the m to the power of -1 for this problem, for the second portion. We were just using it for the first portion.
Yeah, the first portion was finding the units of B. Yeah, and then this is separate. This is then just using that fundamental shear equation and then doing the calculus there and plugging it in. All right. I'll leave it up there for a couple more seconds if you want to write anything down, and then I'll switch the page. All right. So, okay, we'll go on to problem 4. Okay, so for problem 4, we have this figure, and so we have this pressure system with 3 different fluids. We have water, oil, and mercury, and we know 2 points, A and B, and we have some measurements to the interfaces between these different fluids. And what we're looking for is hey, welcome. No, you're good. You're good. Long time no see. So we're on problem 4. We did problems 1 and 3, and then I skipped 2 because I need to come back to that here in a second. But so we're doing 4, and then 5 will be more in depth. But yeah. So we have the system, like I was saying, and we're looking for H, which is the distance from point A to the interface between the water and the oil, and we know that the pressure difference between these two tanks is, which I'll call it, delta P, pressure difference. That's 95,000 pascals. And it says to assume that all fluids, I'll write that clear, all fluids are at 20C. That is because of the table we're going to use. So we just need to know that we have standard temperature for this table so that we can go look at the table for values. And then, yeah, so I guess that's really all we know. So then our find, we're looking for that H value, which is there on the figure. And so for the solution, we are going to write a pressure balance here. So the way we're going to do this is we're going to start at one point on either A or B. We're going to start at A, and then we're going to work our way around this system, and we're going to sum up the pressures and then solve. So the way we start is we say, okay, we're starting at A, so we write the pressure at A, and then we start to move around the system. So as we move up, we're going to subtract pressure because we are, as you're moving up, you're going from higher pressure to lower pressure. So you're subtracting pressure. And then once you start moving down, we'll add pressure because you're going from a lower pressure to a higher pressure. So, okay, so we're starting at A. So we're going to move up from A to the interface between water and oil. We're going to move from interface to interface. So we have PA minus, that's that minus because we're moving up. And then this is going to be, because it's water, that pressure there is going to be the specific weight of water multiplied by the height of water, H. Then we're going to move from, I'll mark it on here. So that was moving from here, this level, to this interface. That's that first term. Now we're moving from this interface, and maybe I can do it in different color, so it's clear. So now we're going from this interface to this interface here. Okay. So that's going to be minus the specific weight of oil multiplied by the distance that's there, which is 0.18 meters. I just switched the units there from centimeters to meters. And then this top portion up here, this guy, let me change color again. Okay, so this portion here we ignore because we're not changing fluids. Okay, so the interface of the mercury is on the other side below that, so we just ignore the top portion. So we go to the next interface, and that guy here. So now we're going from this interface all the way down to this point here, B. And that is going to be added because now we're going down in the fluid. And it's going to be the specific weight of mercury times that distance there, which is 0.18 meters plus H plus 0.35 meters. And then that whole side of the equation is going to be equal to the pressure at point B. So now if we do a little bit of rearranging, we can move PA over. So now we have PB minus PA is equal to negative gamma for water, H, minus gamma for oil, 0.18 meters, plus the gamma for mercury times, I'm going to combine these terms to make it a little bit more readable. 0.53 plus H. Maybe I'll go ahead and write meters here. Meters plus H. Okay. So now we can recognize that PB minus PA, this is that delta P that we were referencing earlier. Okay, so this is 95,000 pascals. That's that value. And so if we look at this, then we can say, okay, we have these H terms we want to solve for, but we also have these gamma terms. So how do we find those? So the gamma terms come from the gammas are from the table, and I believe it's table A6. Let me make sure about that. Table 1.4, that's what it is. So table 1.4 is where these values come from. And so if we go to that table, then we see that water has a gamma value. I actually might have grabbed the wrong table here. Let me see.
Water density.
Yeah, I'm looking for the specific weight, but I think when I did this, I grabbed the wrong table to put on here. Do what? 2.1. Okay. Then I'll pull it up on here real quick and get those values. Specific weights.
Because gamma is rho G.
Mhm.
Yeah.
Yeah.
Yeah, I think you
Right.
got it right there.
Right.
Yeah,
Yeah. So I guess we could just calculate like that, right? Too. So okay.
Because it's
Um,
meters also, so you could just use that.
Okay. Yeah, that works. So we just do the density times 9.81. Yeah. Okay. I'll just do that then. So then we know that gamma. So gamma is equal to rho times G. And so if we have our densities from table 1.4, then we can calculate those. But there's also a table, I think you said 2.1, where you can get the specific weights directly. Okay, so then for water, I think it said 998. Yeah, 998 kilogram per meter cubed. Times 9.81 meter per second squared. Okay. And that's going to be 9790. Okay. And the units there would be Newton per meter cubed. Then we can do the one for oil. Now it doesn't say what type of oil, it just says oil, but it does give a specific gravity. So what we can do is we can just multiply the specific weight of the water by that specific gravity of oil, and that'll give us the specific weight of oil. So this would be 9,790 newtons per meter cubed multiplied by 0.827. Which is going to give us 8097. Oh no, 8097 Newton per meter cubed. And then for mercury, go back to table 1.4. And so water came from this row. Mercury is right here. So mercury's density is 13,550 kilogram per meter cubed. So this would be 13,550 kilogram meter cubed multiplied by gravity, 9.81.
Excuse me.
Yeah.
On the table, it says 13,580.
Oh, does it?
It
Did I get it wrong?
1.4. Oh, 550. Oh, I have a different table in front of me. Sorry.
Oh no, you're good. You're good.
Like,
Thank you
yeah,
for.
that's okay. You can keep using that for now.
Okay, sounds good.
Okay.
Okay, so then we multiply by gravity, meter per second squared, and that's going to be equal to 132,926. Newton per meter cubed. Okay, so now we have our three specific weights, and we know our pressure difference. So the only other unknown is our H value. So we just got to solve for that. Okay. So I'm going to switch pages here. And we will say that 95,000 Newton per meter squared, I switched it from pascals to that, is equal to negative specific weight of water times H. So it'd be minus 9790 Newton per meter cubed multiplied by H minus, and then we have the specific weight of oil times 0.18 meters. Oil was 8097, be 8097 Newton per meter cubed times 0.18 meters plus we have this term plus the specific weight of mercury times 0.53 meters plus H. So the specific weight of mercury is 132,926. Newton per meter cubed. Okay. Newtons per meter cubed. And that's multiplied by 0.53 meters plus H. And now we just solve. Okay, so let's combine our like terms here. So I'm just going to clean this up for a second. So 95,000 newtons per meter squared equals to I'm going to distribute these terms first. So we have 9790 newtons per meter cubed H minus, I'll combine these terms, 8097 times 0.18. That's 1457. Okay. And I'm rounding a little bit here just to make it look a little bit cleaner, but you don't have to round. So 1457, that would be newtons per meter squared plus distribute this term. So we have 132,926 times 0.53. That's going to give 70,451 Newton per meter squared plus 132,926 times H. And that is Newton per meter cubed, that term. So now we can go ahead and combine these together and say that we would have, if we move our just constant terms to the left-hand side and keep our H terms on the right-hand side, then we can say that 95,000 plus 1,457 minus 70,451 is 26,006 Newton per meter squared, and that's equal to 132,926H minus 9,790H, which is 123,136H Newton per meter cubed. So now we just solve for H, and H is going to be equal to 0.211. And that will be in meters. So the good thing about doing the units as you go is that if you end up with meters, then that at least is one check that your answer makes sense. If you ended up with like seconds or inverse meters, and then you're looking at the problem going, that doesn't make sense with what we're supposed to be looking for, then it's a good way to check yourself. Yeah. Sure. Yeah, no problem. Yeah, are there any questions about problem 4? Okay, well, if there aren't any questions, I'm going to move on to problem 5. I think problem 5 is going to take the rest of our time. It's a bit involved. So what I'm going to do is just go ahead and go through it. But then I will record problem 2. Oh, yeah, go ahead.
I had a question.
Yeah. Sure. This page? Sure, that one.
When you multiply the 998 multiplied by the 921,
Yeah.
wouldn't it be meters squared everything?
What I did is I combined the kilogram meter per second squared into newtons. And then I just kept meters cubed.
Oh, okay.
Yeah. So I just did like a little combination there. So yeah, so problem 5 is the most involved problem. So I'm gonna go ahead and start working it. And then I'll go and finish it, but if you need to leave, then feel free to just go ahead and go. I don't want to hold you over, but then what I'll do is I'll go and stop it and I'll record problem 2 and I'll upload problem 2 as well. That way you have all 5 problems. So, okay.
I
So problem.
actually did have a question.
Yeah. What's up?
So,
Go ahead.
so anytime they use like oil, they give like a specific gravity because they don't tell us what kind of oil. In any case, like if we got something else and it was like specific gravity of something that's not in our list, do we always multiply it by the density of water?
Yes. So specific gravity, the definition of that is it's a ratio of the density of whatever substance it is, oil or mercury, relative to what water is. So I'll write it right here. So specific gravity is the density of whatever it is that you're looking for divided by the density of water. I'll write H2O there. Or you could write the specific weight of whatever it is divided by that of water. And that's because these gamma terms, right, are rho G. And so you can cancel the G, and it's that same ratio of density.
Thank you.
Yeah, no problem. No problem. Hope that answered what you're asking about. Okay, so cool. So if you have any more questions about that, just let me know. But all right, so problem 5. So this problem is it's a hydrostatic force balance, and so what we have is we've got this tank that's divided in 2 by a gate. The gate has a hinge at point A, and point B is not fixed, so it can move. The surface, that bottom surface that B is on, is smooth. That's not explicitly stated here, but this surface is smooth. So you could say like no friction is the significance of that. Okay. So essentially what that means is that if we drew this gate, and up here is point A, and down here is point B. Here's point B down here. Our force in the x direction at B, I'll call it Bx, is equal to 0. That's what I mean by no friction. And so the only force that might act on B is going to be in the vertical direction, By. And so we have this gate. It weighs 180 kilograms, and it is 1.2 meters wide into the page. So it's 1 meter in length, and then normal into the page, 1.2 meters. And we're wanting to determine if there is a water depth on the right-hand side, that H value. This water depth is H. That would lead to a force of 0 at point B. And that force that I'm talking about is that By that I wrote over there. And then we want to find that depth. So we're given that we have a mass of 180 kilograms. We know that this, I guess, the width of our gate is equal to 1.2 meters. And we know that we're given our moment of inertia formula, BL cubed over 12. And that's what we know. So then we want to find is there an H where the force at B is equal to 0, and then find it. So I guess spoiler alert, there is a depth of H that'll give you 0 at point B. So that is the case. So I guess you just work this And then if you find it as you work it, then you're kind of answering both at once. But yeah, so alrighty. So I'm going to draw a picture here that will hopefully be helpful. Okay, so I mentioned we have this gate, right? And it's sitting on this floor here. And so if we're thinking about this in terms of forces, we're going to have a force from the, I'll do it this way. I'm going to draw this as a line. Okay, so we have this gate. It's this line here. Here's B. Then we have our floor like that. We have our hinge at A. So we're going to have a force from the glycerin, and we're going to have a force from the water. Do you have a question? Okay. And then our center of gravity here is at the middle of this gate. And we have, so these forces are acting at their centers of pressure, right? So then we have these like distances back to our hinging point that I'm going to call L, LW, and LG for glycerin. Okay, LG. And what else do I want to say there? We know our angle is 60 degrees. Okay, 60 degrees. Yeah, so that kind of shows you the idea here. We also have a weight. So we have the weight of this thing, W, that acts at the center of gravity. And so that's kind of like most of our forces that are going to matter. It could be worth noting that we're going to have reaction forces at A. They're not really going to come into play in the problem, but I'll call them AY and AX. And that's because that hinge that's there. AY, AX. Okay. So that is pretty much what we need to know. Okay, so what we're going to do is we are going to compute these forces and their lines of action. So essentially the layout of this problem is we're going to compute these forces, and then we're going to compute the lines of action there, these L values. And then we're going to sum the moments about A, which is why I said that the A forces don't come into play, because they won't affect your moment sum. And then that balance of moments is going to let us solve for the total H value. And so I'll dive into that. All right, so if you were to take the values off that table 1.4, you would find the specific weight of glycerin to be, rho glycerin times gravity, and that is going to come out to 12,360 Newton per meter cubed. And the one for water is going to equal to 9,790 Newton per meter cubed. And so that's just for reference. And then we need to know the distance up for the height of the center of gravity from the top of this gate, right? So if we went back to our picture here, then we are looking for what's this height? What's that value? HCG. Okay. So that is going to be, we have the 60-degree angle here. So if you were to think about that angle being right here, 60 degrees, then that height is going to be the sine of 60 multiplied by half of the length of the gate. So HCG is equal to 0.5 meters sine 60 degrees. And that is going to give you 0.433 meters. So that's the vertical height. Now, then, that is the HCG local to the gate. So for the water, when we're calculating our force, what we need is, for the force calculation, is this HCG water. That's the value used for the water force calculation. So HCG of water is going to be equal to, oh no, I'm sorry, that's glycerin. Glycerin. Okay. So the glycerin is going to be 2 meters minus 0.433 meters, which is 1.567 meters. Okay. So then, if we compute the glycerin force and line of action, we know that force is pressure times area. So then the force of glycerin is going to be the pressure of glycerin. Pressure is your gamma, specific weight of glycerin, multiplied by that HCG of glycerin, multiplied by the area for glycerin. And so that that value there, when you plug in the values, is going to be 12,360 Newton per meter cubed times 1.567 meters times 1 multiplied by 1.2 meters squared. And that will give you 23,242 newtons. There it is. Okay, that is the force of glycerin. Now we want to know the line of action as well. So for the line of action, we are going to calculate the YCP value. We know that YCP is equal to negative I XX sine of theta divided by HCG times A. So I'm going to move over here to keep working. So that value is going to be negative BL cubed over 12. That's your moment of inertia formula, times sine of theta divided by HCG glycerin times the area of glycerin. And so if we plug our values in there, we'll get negative. The base of this gate is 1.2 meters. The length of it is 1 meter. cube that, divide by 12. Our sine is sine of 60 degrees. And divide that by the height center of gravity of glycerin, 1.567 meters, multiplied by the area, like that. And when you calculate that whole thing, then you're going to get that that value is negative 0.0461 meters. That's your YCP glycerin. And so that's saying that, just to review, that the center pressure is 0.0461 meters below the center of gravity, is what that's saying. So, pictorially, what that's saying is that this distance here, that distance, is your YCP for glycerin. Okay, so then we need to calculate okay. I was reviewing that, make sure I'm on track with what I want to say. Okay, so now we want to do the same for water. So the force of water is going to be, the same pressure of water multiplied by the area of water, which is going to be the specific weight of water multiplied by the height, center of gravity of water, multiplied by the area of water. Okay. And so that is going to come out to, if I plug in some values here, this will be 9790 Newton per meter cubed. That is the specific weight of water. The area is 1 times 1.2 meters squared. And then we have this HCG of water, which is our unknown. Because we're looking for the total height of the water, and this is a part of that total height, this HCG water. So we're going to leave that unknown. And maybe to give some reference to that, that distance there, this is HCG water. So we have to find that, and then we'll use that to find the total H value. Okay. So then if we write our line of action distance for water, that's my bad, YCP for water, we'll use that to find the line of action. Then that's going to be the same negative BL cubed over 12 sine of theta over HCG water, area of water. And that's going to be the same negative 1.2 meters times 1 meter cubed divided by 12 sine 60 degrees divided by HCG water times that 1.2 times 1.0 meter squared area. And that will give you 0.0722, so negative 0.0722 over that HCG water. And that whole thing is in meters squared because we don't know that HCG water yet, because this will be in meters HCG water, so that'll cancel one of those meters if we had a value. All right, so then that means that we've calculated our YCP values and our forces for both of these fluids. I'm just underlining them as I go. And so now that we know kind of like what these forces are and where they are, then we need to do a moment balance. So we're going to, I'm going to switch pages. We're going to sum the moments around A and set that equal to 0. And so if you look at the picture, the force of glycerin, if you use right-hand rule, is going to give you a positive force, a positive moment. The force of glycerin is a positive moment. The force of water will be a negative moment, and the weight will end up giving you a positive moment. So we have those three forces in this balance. Okay, so if we sum this up, we'll have 0 equals 2. The force of our glycerin. Yeah, okay. Force of glycerin was 23,242 newtons. Okay, then its line of action is going to be, or its moment arm is going to be the length from the center of gravity to the hinge plus that YCP value, because that's what, yeah, it's this right here. It's this distance, that's 0.5 meters plus this distance. That's what we're getting there. So this is going to be 0.5 okay, 0.5 plus 0.0461, that's meters. Then we're going to subtract out our water force, which is 11,748 Newton meters HCG water multiplied by 0.5 meters plus 0.0722 over HCG water. And that was meters squared that I wrote there, meters squared. Okay, and then we're going to add on to that the effect of our weight. The weight term here, if our weight is acting on this bar at the center of gravity, you could rewrite, you could draw the weight like this, and then you could say there's a component in this direction and a component in this direction. This angle here is 60 degrees. Okay, so then the weight in the, this is weight in the, we're looking for this, I'm going to say it's weight normal, WN, weight normal to our surface. So WN is going to be W cosine of 60 degrees. Yeah. And then the moment arm here, this distance is 0.5 meters. Okay, so then this would be the weight cosine 60 degrees times 0.5 meters, and the weight value is going to be that 100 and I believe it was 80 kilograms, 180 kilograms times gravity. Okay, so then that, if we kind of sum some of that together or combine those terms, then we're going to get that first term goes to 12,692.456 Newton meters. The second term is going to it's going to break down a little bit, I guess. I'm going to just distribute that second term, and so that's going to go to 5874 HCCGW plus 722 848.2. Okay. And then we're going to add to that, we have this weight term, 180 kilograms times 9.81 times 0.5, which is 882.9. I feel like there's something I haven't done here. Oh, I left out my cosine of 60. That's what I did. I forgot to multiply this by cosine 60. So it's the 180 kilograms times 9.81 times the cosine of 60 degrees times 0.5. There we go. This is 441.45. Okay. Does that make sense? Everything there? Okay, cool. So then what we're going to do now is go ahead and solve for that HCGW value. Yeah, so we'll move this side over, and that will be equal to 12,692.456 plus 848.2 plus 441.45 should give you 13,982.106, which would mean that HCGW is equal to 5874. I got a wrong quantity for some reason. Give me 1 second. I'm going to see if I can figure out why that value is not coming out right. That's correct. That's correct. Oh, this is why, I guess. This value here should be negative. Yeah, let's see if that fixes it. So we'd have 12,692.456 minus 848.2 plus 441.45. Yep, that's what it was. Okay, so I just forgot to distribute my negative correctly, which is all too easy to do. So I have to watch myself there. So we have 12,800 or 12,285.706. And then when you divide those values, you'll get that HCGW value to be 2.09 meters. Okay. So one last step here. Like I said on the picture, that HCGW value is from the surface of the water to the center of gravity of this gate. And so we need to know what this extra little bit here is. What is that guy? So that is just going to be that 0.5 sine of 60 value again. So yeah, half the rod sine 60, right? Okay, so then for our final answer, H is going to be 2.09 plus 0.5 sine of 60 degrees. And that will give you 2.5245 meters. And that is your final answer. And I guess you could write, yes, there is an H where by equals 0. Okay. So do you have any questions about any of that?
Can you go for the force of the weight again?
Yeah. Yeah. So yeah. So if we have our rod, right, and our weight is acting at the center of gravity, then if we, we know that this angle here is 60 degrees. What helps me is if I break that force into a component that's normal to this gate, and then one that's parallel to it. And so that would look something like this. And we could call those W parallel and W normal. And so angles can be really tricky to, so the way that I would do it is say, this is 90, which means that this is 30. And then this has to be 90. So then that's 60. And then say that the, what would that be? Cosine? Cosine of 60 is going to be adjacent over hypotenuse because we want that normal weight value. And then just rearrange like that. Cool. Any other questions?
It might be dumb, but what's like a reason that you wouldn't be able to find an H?
That's a good question. Let's see. So it's saying you want a force at B to be equal to 0. So a force at B equal to 0 would mean that
It's like stationary, right?
right. Yeah, there's no. I mean, I guess you could have a force at B, but if you had a force at B, it would show up in that moment summation. It would play a role. But since we didn't include it at all in the summation, we're saying, okay, it's 0. So then what forces from the water and glycerin would make that be the case? You know, or what? Well, we know the forces. What height would satisfy that
So it's not
requirement?
gonna be like any question where it is like,
I don't think so.
yeah.
No, I mean, because unless there's a restriction on the water, like if he was saying like, you know, the water is limited to a 1.5 meters in height, and then you found it to be 2 meters would be the satisfactory height, then you might say that you would need a bigger tank to be able to satisfy it. But I don't think that there's really a way that you wouldn't be able to find an H. So yeah, and I know we're over. So what I'll do is I'm going to go back and solve problem 2, and I'll upload it as another video. That one is let me go back to it briefly. It's a rotating disc in an oil, and it's, if you remember the derivation of the shear stress, where you you have a differential ring element on the surface of the disc, and then you do the whole integration with radius, and you find that torque value, I believe is what I was asking for. Yeah, the torque. And then, so this is basically just like that, but because you have oil on both sides of the disc, you multiply the derivation by 2 because you have both sides. But I will go back and record a video. That way y'all aren't having to stay here, and I'll upload it and show that derivation. Okay. So I'm going to go ahead and shut this down. But thank you all for being here and for staying.
Thank you.
Yeah, of course. Of course.
Thank you.
Yeah, no problem. Thanks for coming online. Hope it was helpful.
Thank you.
Yeah, you're welcome. No problem. This always says, do you want to keep your ink annotations? I'm like, I better click keep. If I clicked discard, I'd be so sad. Yeah, you too. Thanks. Oh gosh. It's be like, nope. Yeah, that would not be good. Okay. Yeah. Let me stop this recording real quick. Yeah, no, you're good. You're good. I'm gonna let this start.
Thank you.
Yeah, you're welcome. Have a good one. Okay, stop recording. Yeah.